Hello, everybody. We're group 10 of CSML 1000, and the final project that we have chosen is NBA shot prediction. The members of our group are Alex, myself, Patrick, Tony, and Viswish. And essentially, this project predicts from any point on the court your likelihood of going into the basket while shooting. So the abstract of our project is as follows. So the use of various predictive metrics in sports has been occurring as long as human beings have watched each other compete. Initially, this started out as a simple gut feeling or a subjective assessment of the competitors. The bets usually go to the bigger fighter. In more recent times, humanity has refined its predictive power with the advent of statistics and logical decision making, which was famously put to use in Major League Baseball, as shown in the film Moneyball. With the advent of the information age and the possibility for large-scale data analytics and machine learning, the National Basketball Association, or NBA, has decided to pursue this analysis to better understand player matchups, defender versus offender, and to assess and optimize shooter performance. So as we go into the business understanding, I'm going to speak a little more about detailed statistics. The detailed statistics are already available to the MBA as they've been tracked for many years, supporting classical statistical decision making. The goal is to run both unsupervised and supervised machine learning algorithms on the statistical data available. In technical terms, we aim to deliver predictive metrics for threat benefit level at an individual player level, as well as an interactive application that identifies the likelihood of a shot landing from a specific offender shooting from a specific position on the court against a specific defender located a certain distance away. This will allow coaches to run limited scenarios in the predictive model to inform both their practice routines and to assist in making strategic decisions during live games. As an example, let's consider the matchup of LeBron James on offense and Serge Ibaka on defense. Let's assume that LeBron typically tries to shoot from the top of the key and is being defended by Serge Ibaka 5 feet away. The model takes these discrete inputs and outputs a real-world percentage success of 10.5%, for example. If the average shooting success rate is 30%, we can identify this as a bad shot and encourage LeBron to pass in these situations. And now I'm going to turn it over to my group member, Vis, to talk about our data understanding.
Thanks, Patrick. So we'll begin with understanding each feature available in this data. And the available data set is the data containing all shots attempted at NBA games in the time frame of 2014 to 2015. So for each shot attempted, the most important outcome of that attempt, whether the shot was made or missed, is available. This is seen in two columns, shot results and FGM, where FGM stands for field goal made. In support of this outcome, there are a number of other data points to be seen, like the player who attempted the shot and who defended the shot. How far away was the defender? How far away from the basket was the shot attempted from? Was a match at home or away location, etc. So with that understanding, let's look at a quick summary of the data. So we have game ID, which is a unique identification of the game. And then the matchup says the date and the teams the match was between, and some of the other features that I just touched upon. Moving on, if we could scroll a little further, we'll take a look at the data dictionary. So in all, we have about 21 features in this data set, starting with game ID, like we just saw, which is a unique ID for each game. Matchup shows the date of the match and the teams the match was between. Location, A stands for away and H stands for home. So the location of the match is shown with respect to the first team in the matchup column. So it's the home or away location of the team that's first featured in the matchup column. W is a win or loss. W means win, and L means lost. Again, this is with respect to the first team in the matchup column. Final margin is the difference in points between the teams at the end of the game. Shot number, to be read in conjunction with the period column, indicates the shot number in a given game period. and period indicates the game period. Game clock is the time elapsed since the period commenced. This data set shows the time at which the shot was attempted. And what's to be noted is that each period in a basketball game, in an NBA game, has 12 minutes. The length of time given for each shot is shot clock, and there's a maximum of 24 seconds rule in an NBA game. Dribbles is the number of times the ball was dribbled before the shot was attempted. Touch time is the length of time a player touched the ball or was in possession of the ball. Shot distance is the distance from which a shot was attempted. Distance is expressed in feet. PTS_type is points awarded if a shot was made. So we have either a 2-pointer or 3-pointer shots in this game. Shot result is this field indicates whether the shot was made or missed. Closest defender shows the name of the player that was the closest defender to the player who attempted the shot. And we have the unique ID of the closest defender. And close def dist is a column that says the distance at which the closest defender was from the person who attempted the shot. FGM, again, abbreviated an abbreviation for field goals made. This can also be looked at as a proxy for the shot result column that we already saw. PTS is the points awarded for the shots made. Player name is the name of the player who attempted the shot and that person's ID. With that understanding of the data, I now turn it back to Patrick to walk us through some plots.
Thanks, Vis. We're just going to have a quick look at some histogram plots of some of the most important features in our data set. This will allow us to get a better understanding of how the data is distributed. So the first one we're going to have a look at is the closest defender distance histogram. So this is a plot of how far away the defender was from the person attempting the shot. So looking at the plot, we can see that a majority of the shots were defended from within 5 feet of the player attempting the shot. And it's safe to say that more than 90% of the shots were defended from within 10 feet. Moving on to the next plot, which is the dribbles histogram, we can see by this count that measures how many dribbles the shooter made with the ball, that most shots were attempted soon after getting the ball, and that more than 80% of the shots were attempted within 3 dribbles, which is quite soon. Moving on to the next plot, looking at the final margin, which measures the difference in score between the two teams at the end of the game, we can show that most matches were won or lost with a 15-point margin. So not a lot of ties in there. Moving on to the next plot, the shot distance histogram shows that most of the shots were attempted from about the free throw line there at about 25 feet. But we can see that, as you might expect, as you get closer to the basket, the number of attempted shots goes up. So fairly logical, but interesting to note about that free throw line. And with that, I'm going to pass it off to my colleague Tony to talk a bit more about our data preparation steps.
Thank you, Patrick. So as with any data set that we can get publicly, the quality isn't always there. There's always going to be missing data, invalid data that really doesn't make sense. And so when we were looking at the data, we were going through and actually looking up the definitions of some of these things and finding that some of them actually don't make sense. And so the first thing was the shot clock. And so the shot clock counts down from 24 seconds towards 0. And actually there is something in the shot clock that did make sense. There were a lot of NAs and negative values actually. And so first thing we did was actually to remove all the negative values because shot clock really shouldn't have negative values. The second thing was we noticed a lot of NAs whenever game clock was less than 25. So what we simply did was we took the game clock, it converted to seconds, and whenever game clock was less than 25 seconds, so which is the time left for that period, we simply made shot clock equal to game clock. So the next feature that actually needed cleaning was names, and so we noticed that names had a lot of discrepancies in terms of the format of the names, and so some of the names were actually first name, last name, and the defender names are actually last name then first name. So the very first thing we did was to actually change any format that was first name then last name to last name comma first name, which we did there. And then the next part was actually some names or some parts of the names were not capitalized consistently. So for example, DJ would be like, instead of capital D, capital J, there some of them might be capital D, lowercase j. And so definitely uppercase on everything. The next part is same example, DJ. There might be some names that are D.J. dot and then D.J with no dot, things like that. So definitely we had to remove the dot from the names. And so after that, the name feature was definitely cleaned up a lot. Luckily, there were no NAs. The next part is in terms of game clock. And so game clock was expressed as minute, semicolon, second, 11:00, right? The typical human understanding. However, it's not very useful, especially with the data in R. And so we just converted to seconds. The last thing that we had to change was touch time. So touch time, we noticed that there were quite a few negative numbers and 0 or NAs. And so what we did was, it doesn't really make sense for touch time to be less than 0.1 seconds. So for any touch time that is greater than 0, we kept, and anything less than or equal to 0, we threw away. So in terms of trying to incorporate unsupervised learning, definitely one of the most popular ways to do that is with clustering. And arguably the most popular way is with k-means. And with k-means and clustering, we actually have to find out the appropriate number of clusters. We actually have to define that. And one of the ways to do that is with the elbow method. It is non-computationally intensive, and it is a pretty decent way of finding the optimal number of clusters. And so we can see here that we have plotted number of clusters k versus total within clusters sum of squares. And we can sort of see that, although it's not very clear, that the total within cluster sum of squares starts to, the difference in terms of drop off starts to appear at 3 and 4 clusters. That's where it starts to slow down. And so one would think that maybe 3 or 4 clusters would be ideal. There are other methods of finding the appropriate number of clusters. For example, the Bayesian inference method and the silhouette method to find the proper number of clusters. However, they are very computationally intensive and take a lot of RAM, especially for large data sets like the one that we're using. 56 gigabytes is definitely not within our capability at the current moment. And so therefore we have decided to test out the number of clusters by plotting them and seeing what happens to the data. So that's where we see it in the next few slides here. So this is a plot of pretty much the principal component number 1 versus principal component number 2 with 2 clusters, 3 clusters, and 4 clusters. And you see here that 4 clusters, although it seems like earlier in the elbow method that it might actually start to significantly slow down there, and maybe 4 clusters would be ideal, but it looks very messy here. And so maybe 4 clusters is not the ideal number of clusters. Maybe 3 clusters is better. So let's look at the dribbles versus shot distance and grouped by shot result. So for example, the left side would be shots made, and the right side would be shots missed. And then the X is number of dribbles, Y is shot distance in feet. So you can see here that 2 clusters is pretty good in terms of how the 2 clusters look. There's not too much overlap. It's not a mishmash of colors. 3 clusters is actually pretty good here on the same graph. And 4 clusters, as you can see here, it's really starting to homogenize in terms of colors. So probably 4 clusters doesn't really work, at least for some of the data that we're comparing. So let's see here, the shot distance versus closest defender distance grouped by shot result. So it's a very similar graph. However, it's not with dribbles. It is shot distance and closest defender distance. And 2 clusters here is quite weird. The 2 clusters are overlapping each other. 3 clusters is not bad. As you see here, the blue and green is well defined. The orange is, it's stuck between these 2. Can't really decide which way to go. However, 4 clusters here, it's really when it really doesn't look like 4 clusters is the ideal number of clusters. There's actually a very interesting pattern that we can see here. So shot distance and shots being made and closest defender distance. So we see here that there seems to be quite a few breakaway shots that actually made it in, probably far away from everyone else. And actually, that's actually a very successful strategy in NBA. So the next part, actually, I'm going to have my partner, Vis, who's going to talk about the other unsupervised learning method that we're trying to use to understand more about the data, principal component analysis. So Vis, off to you.
Thank you, Tony. So we used principal components analysis here to see if the data set had any features that were highly correlated. And the idea behind that was to see if we could merge some of them into principal components without losing data significantly. So the PCA algorithm identified 8 important numeric features in this data set, giving us 8 principal components, PC1 to PC8. And investigating these principal components further, we learned that principal component 1 and 2 were the features that were responsible for almost 50% of the variance in the data. And the other principal components from 3 to 8 were responsible for the other 50%. In the graph that you're looking at, this is a biplot of the two principal components, PC1 and 2. And in this graph, it displays the arrow vectors for each feature in the original data set. The way we interpret this data set, this particular graph, is by the length of each of the arrow. The longer the arrow is, the more significant that feature is towards the two principal components, PC1 and 2 over here. The distance from one line to another explains the amount of correlation the features have amongst themselves. So looking at the graph, we can see that game clock and shot clock are highly correlated, but have very minimal effect on the two principal components. Also, we see correlation between closest defended distance and shot distance. Both of these features have medium impact on both the principal components. Some correlation is seen between shot number and the period. Both of these features have quite a significant effect on both the principal components. Lastly, the very highly correlated touch time and dribble have significant effect on the combined features. So with this analysis, we learned a bit more about the individual features and how they impact our data and therefore our prediction. We'll use this information to choose what features we will expose to the user through our application. For instance, exposing either touch time or dribble would likely have similar effect, so we may simply pick one of them. All right, with that said, I would now turn it over to our partner, Alex, to walk us through some more models. Alex, the floor is yours.
All right, thanks, Viv. So in terms of the supervised learning models, we decided to go with supervised learning models that support classification, since the business problem here is to attempt to predict which attempted shots can be converted into field goals made. The four models we chose to, just try and test out were decision tree, logistic regression, GBM, and GBM with the principal component analysis stuff that Tony worked on. We chose these models particularly because they're fairly easy to explain, especially the decision tree and logistic regression. And so before we ran the models, we first explicitly converted the predictors and response variables into the correct data type. So for example, shot distance, which is the distance from the player who shot the ball into the net. It's a numeric factor. And FGM, which is our response variable, is categorical. There's no need to undersample the majority class or oversample the minority class, because the split was roughly 55 to 45%. So there's no need to do that. Lastly, we split the data set into a training and testing set, around 70% training and exactly 70% training and 30% testing. So for the first model we'll talk about briefly is the decision tree model. It's a very simple algorithm. You have like a tree-like structure. Essentially, there's a root node that splits into the branches, and each branch contains, or sub-branch contains a decision node, and it either ends in a terminal or another decision node, so it can keep going on multiple layers. Like I said, it's fairly easy to explain, and it's very easy to visualize. So that's the first model we chose. So in terms of the most important variables for the decision tree, we found were shot distance and the closest defender distance, and that's why there's only like 2 layers. Essentially, we found that other the predictor variables weren't as important, and as a result, you can see there's like just only 3 end nodes, and it's kind of interesting because you see that they're very similar to the free clusters in the unsupervised learning, and that's how they're related essentially. Yeah, in terms of the AUC curve, we'll just show it very briefly here. So results were not spectacular with AUC of 0.594 under the sensitivity and specificity curve. Can't speak tonight, but yes, it was a 0.594. So it wasn't spectacular, but it's actually, interesting thing is compared to the other models, it was actually roughly the same. Yeah, the second model we did was the logistic regression. So logistic regression is like a type of parametric model, and which is based off of the logistic function. We made a few assumptions with the logistic regression. Well, there are a few assumptions, and so the first one is that there's enough observations for a large data set, which is true. In our case, it was more than 100,000. The second assumption is that observations are independent of one another. The third assumption is response variable, it has to be binary, 0 or 1, which is true because we have a field goal made of 0 or 1. Fourth, the predictor variables are related to a logit function. And lastly, there's minimal multicollinearity among the predictor variables. So here, essentially, we ran the logistic regression. And you can see the AUC was similar at a 0.595. And in terms of other metrics here, the accuracy is at 16%. If you look at the sensitivity, it's interesting, it's 0.7251, and specificity 0.4708. So this means that the model is actually fairly good at predicting, or at least out of all the positive cases, it was accurate in choosing those positive cases, essentially. We chose not to use a logistic regression model because one is that it was actually like a huge model, because we also included the player names. It was actually at, I think, a 1 gig model, so it was not feasible to put it in our Shiny app, and also took a while to train at something ridiculous of 4 hours. So that's why we chose then not to at least go with logistic regression for our Shiny app. The third model we'll talk about briefly is stochastic gradient boosting. So it's a bit more complicated than compared to the last two models. Essentially, you're over numerous iterations, you're trying to improve the weak learners, essentially. And the stochastic part comes when you draw a random subsample from, like, when you're iterating. So hence the name stochastic. So when we initially trained this GBM model, we first decided to keep the closest defender, the player names, essentially, just to like see if they were useful. But in itself, the model was fairly big. It was smaller than the logistic regression. It was at 150 megabytes, but it was still big enough that it would be a hassle to upload into the Shiny app. And at the same time, it provided negligible improvement in the metrics. So we dropped those two columns. And the results are still fairly similar to the other two, but at least it trains faster. And yeah, and so that you can see here, accuracy is 60%, sensitivity 86, specificity 32. Yeah, so we dropped it, and now the model trained in about an hour, if I remember correctly. We did a few hyper parameter optimizations. We found that the interaction depth of 5 and 40 trees and a minimum of 10 observations in each node, with a shrinkage of 0.1 to be the most ideal model. Yeah. And lastly, I'm just going to show the UC curve. Once again, 0.594, it's fairly similar. And lastly, we chose to do stochastic gradient boosting with PCA, principal component analysis, that Tony did and mentioned. My colleagues mentioned in the previous section. So here, essentially, I'm not going to repeat what GBM is. You guys already know. we did GBM for all 8 of the principal components. You can see the relative influence of each component. PC6 was very high, PC3 pretty medium, and then the rest were relatively low. So in terms of the metrics, once again, they're very similar. Scored at 61.5. Accuracy, sensitivity was high as usual, but specificity was low at 0.38. And yeah, the train time is roughly the same as well compared to the GBM model. You can see here AUC was once again very similar. And in terms of the hyperparameter optimization, it was a bit different. It was 100 trees, interaction depth of 5, shrinkage 0.1, and 10-minute observations. Yeah, and yes, as you can see here, all the models were relatively had the same, had very, very close performance. Yeah, and that's it. I'm going to hand over to this.
Thanks, Alex. So moving on to the evaluation of the models and talking about some ethical considerations. So in terms of evaluation, all models perform fairly similarly in terms of metrics such as the ROC curve, area under the curve, accuracy, balanced accuracy, sensitivity, and specificity. In terms of overall performance, the models were not spectacular, so to say. They showed an accuracy, balanced accuracy, and AUC of around 0.6, with sensitivity of around 70 to 80%, and a specificity of 30 to 40%. Nevertheless, there were some positives to be noted. Although the model was only 10% better than chance, the sensitivity of all models were quite high at 70 to 80%. This meant that the model was fairly good at correctly predicting the percentage of actually positive cases, which is field goals made in our case. But on the flip side, all models had fairly poor specificity, meaning the models were not so good at correctly predicting the percentage of actual negative cases or field goals missed. Moving on to some ethical considerations in this project. As with any data set that includes specific data on real people, we have exercised utmost care and considered the impact of our prediction on individuals. We have specifically chosen to exclude player name and defender names from our application in consideration of possible discrimination against any individual. Instead, we present our application as a generic tool to be used for any kind of basketball decision making, like determining the best positioning, post-game review, testing new strategies, etc., and not to judge specific players. When using our application to predict shot percentages, it is important to remember the data set on which it is based. As a purely NBA data set, it is only applicable to NBA players and should be used only within the premise of NBA and not be used for other leagues such as the NCAA or WNBA, where player characteristics, court specifics, and rules, etc., are different. There is a risk in this predictive model being applied incorrectly, which is why we have tried to explicitly specify that this is an NBA predictor only. That said, we'll move on to take a look at the app on Shiny, and I will turn it over to Patrick.
Okay, thank you very much, Fis. Now we're on to the exciting part. This is our Shiny app, and this is what the end user interface is going to look like. So you can see here that we've simulated a basketball court. This is an NBA regulation court. It's 94 feet wide by 50 feet high, and we have scaled everything appropriately there. So as you move your mouse over the court, you'll notice just below, the hover position indicates exactly where you are. So the origin is at the top left here, which is 0 by 0. And as you get further away, the amount of feet increases. So you can see the court is 50 feet long, and 94 feet wide in the X. So you place the shooter and the defender on this court, and then the app will automatically output a prediction. And the way you do that is by single clicking to place the shooter and double clicking to place the defender. And we need both of those placed to output a prediction, because otherwise there's insufficient data to run the prediction algorithm on. So let's have an easy shot first of all and put the defender right up near, put the shooter right up near the basket. So I'm going to single click near the basket here. And you can see that the shooter position has been specified here on the left. The shooter's at 9 feet from the origin and about 25 feet in the y-axis. And I'm going to put the defender very far away. Let's say he's on the other end of the court. So this should be an easy shot. So I'm going to double click to place the defender here. So predicted likelihood of scoring has now appeared, and you can see that that is 81.94%, which is a pretty good shot. So we would recommend that if you're in this position, you definitely take this shot. You notice some extra information has popped up here as the defender position is at x84 and y equals 24 feet, so very far away on the opposite end of the court. The distance to the basket, which is the distance from the shooter to the basket, has been measured at 4.02 feet. And the distance from the shooter to the closest defender, remember the shooter is here and the defender is over here, is 76 feet. So you can see if we reset all of this, I'm going to place the defender, let's say at the top right. I'm going to place the I'm going to place the shooter at the top right, and I'm going to place the defender just about right next to him. So we can see that the distance from the shooter to the defender is only 1.6 feet. The predicted likelihood of scoring here, very low, 13.14%. But let's see what happens when we walk the walk the shooter closer to the basket. So I'm going to click over here, bring a little closer. We can see that probability starting to increase. And it increases and increases. Shooting from behind the half-court line, not usually a good idea, but let's bring it up a little closer. And as we start to get into common shooting distance here, where most of the shots are taken, it'll really start to go up. Inching closer and closer. And as we get near the basket, we get a massive increase there. Now, for a final example here, let's look at what happens where we place the shooter right next to the basket. Let's say here, I'm single clicking there, and let's put the defender right next to them. So right now, with the defender far away, the predicted likelihood of scoring is 54.27. So let's see what happens when we put the defender next to him. That is a significant decrease. So that decrease right there is explained by the negative influence of the defender trying to block the shooter. So you can see it's a pretty powerful tool. You can play around with both shooter and defender position. And we've also got another few filters that are available for you. So looking over at the left here, we've got shot clock. So this is the number of seconds that you have remaining to shoot. We have game clock. That's the number of seconds that have elapsed total in the period, seconds remaining in the whole period, and you can select the period. So a typical basketball game in the NBA has 4 periods, and then you're allowed to go into 5, 6, and 7 of overtime. So let's run a quick example with one of these. I'm going to put the defender right about here, not too close to the basket, not too far, the shooter, and I'm going to put the defender a little further away. So as we increase the shot clock, let's start at 24, let's say, 24 seconds remaining to make a shot. Your likelihood of scoring is 45%. So let's reduce that by a few seconds. Time is getting shorter. Your likelihood of scoring has now gone down to 43%, so we're decreasing. Let's go to 6, 41%. Let's go to 2, 39%. Let's go all the way to 0, so you have to shoot immediately. 25%. So you can see here what an impact the amount of time that you have left makes on the likelihood of you actually scoring. So resetting that again, let's do a game clock example. So I'm going to put the shooter here and the defender fairly close by over here, and we'll see what game clock matters. So starting the game clock at 0, which means that there is no time left in this period. Let's start it at 7:20. So at 7:20, you have a 24.87% chance of scoring. Let's reduce it by, say, half, and we'll predict. Not too much difference, and we reduce it to almost no time left. You can see that as the game clock runs out, your likelihood of scoring goes down. This isn't as significant an impact as the shot clock, but significant enough for us to include it. And a final example, let's put the defender near the basket, or sorry, the shooter here, and put the defender over here. So period 1, we have a 36.82% chance of scoring. Let's go all the way to the last period and see if anything happens there. Not in this particular case. We've noticed in some cases that period 4 tends to reduce the overall chance of scoring. So let's see if we can get it here, but if not, no worries. Yeah, there we go. So in period 1, we've got a 26.25% chance of scoring. If this same situation with the shooter here and the defender here were occurring in period 4, our chance of scoring would actually go up in this case. So it's not always entirely consistent. You should play around with periods and see what works for your strategy and if that has an impact to you. So in general, challenges with this app, we initially tried this with the regression tree model, but it wasn't quite fine-grained enough for the probability kind of predictions we were looking at. So we moved to the gradient boosting model, and we're very happy with the fine-grained kind of percentages we're getting with gradient boosting. As you move the shooter around, you can see that we get pretty good percentages. So all in all, I think that we've produced a pretty valuable tool here for NBA coaches, and it's fairly intuitive in how you use it. You can simply single click to place the shooter, double click to place the defender, and you don't have to use the rest of the filters if you don't want to. Okay, that concludes our presentation. We hope you've enjoyed. We are fairly proud of the tool that we've produced here, but there's always room for improvement. So we really look forward to any feedback you guys can provide on this. Otherwise, have a great day.